Hello. This will be a demonstration of Proposition 2 from Book 10 of Euclid's Elements, which says that if the lesser of two unequal magnitudes be continually subtracted from the greater, and yet the remainder never measures the one before it, the two given magnitudes are incommensurable to one another. That is to say, they have no common measure. We're given two unequal magnitudes, AB and CD. And again, these magnitudes don't have to be straight lines, but I will be representing them as straight lines for Book 10. But the point is they're just two magnitudes of the same type, so they're like both straight lines, or they're both angles, or they're both areas. And the point is that they are also unequal to each other, and in this case we'll have AB be less than CD. And what's going to be the case about these two unequal magnitudes, AB and CD, is if we continually subtract the lesser from the greater, the remainder will never measure the one before it. I'll go more into detail what exactly this is going to look like, but for right now, I'll just say that this is the case. That if we continually subtract the lesser magnitude from the greater, then the remainder will never measure the one before it. If this is the case for AB and CD, then AB and CD are incommensurable. They have no common measure. For if this is not the case, then they are commensurable, and there will be some common measure, and we'll call that E. E will measure both AB and CD. We'll just set it out like so. So we'll have E like this. Now, E is a common measure between AB and CD. What we're going to do next is this process of continuous subtraction, which we saw all the way back in Book 7. In fact, this proposition 10.2 bears a lot of similarities to 7.1. The method is mostly the same, except for a specific quirk of magnitudes and a specific proposition of Book 10. But besides that, the logic is mostly the same. And in fact, you'll notice a lot of similarities between incommensurable magnitudes and co-prime numbers. And in fact, that's going to be one of the themes of Book 10, is number theory relating to magnitude theory. But I won't get into all that right now. What we'll just do is we'll do this process of continuous subtraction like we did in Proposition 7.1. We'll measure CD with AB, and that'll get us to FD like this. FD will be some multiple of AB, and we will leave CF less than CD. Then what we're going to do next is we're going to take this remainder CF, measure AB with it, get a number like, a magnitude like BG. So BG is a multiple of CF, and we're going to have this remainder AG, which is left. Now, we know that if we continually do this process of continuous subtraction, Proposition 10.1 tells us that we'll eventually reach some magnitude which is less than the common measure E. That's what Proposition 10.1 is all about. It's about the fact that you can get a magnitude that is less than any given magnitude. And so because we know that there's going to be some magnitude we'll hit, which is less than the magnitude E, for right now, we're just going to say that AG is less than E. We know a magnitude less than E will exist, so for right now, we're just going to say AG is such a magnitude. But the point is, we'll eventually reach something that is less than E, so we'll just stop the buck here and say that AG is less than E. Now, because E measures AB, that's how we made E in our first step, and AB measures FD, for that's how we made FD in our second step, then we know from a property of magnitudes that E will measure FD. So that's just kind of obvious. A measures B, B measures C, therefore A measures C. We saw this back with numbers, but this is also true of magnitudes as well, as we're seeing here. So because E measures AB, AB measures FD, therefore E measures FD. But we also know that E measures the whole CD. So E is also going to measure, again by a property of magnitudes, the difference of CD from DF. E is going to measure CD minus DF, which we know is the magnitude CF. So E is going to measure CF. But we also know that CF measures BG. That's how we made BG in our second step. So again, by that same property of magnitudes, that because A measures B and B measures C, A therefore measures C. Because E measures CF, as was shown in our third step, and CF measures BG as we created BG in our second step, E therefore also measures BG. But again, we know that E measures the whole AB. That's how we made E in our first step. So E is going to measure the difference of AB from BG, which we know is the magnitude AG. AB minus BG is AG. So E is going to measure AG. But if this is the case, that E measures AG, then E has to be less than AG, and AG has to be greater than E. But we know from our second step, we set out AG to be the first magnitude less than E. So AG is both less than and greater than the same magnitude E, which is obviously impossible. And so we can conclude that no such common measure between AB and CD does exist, and that therefore they are incommensurable, which is what we set out to prove, which means we're done with the proposition, therefore, etc., QED. I do want to say a few things about this before I end the video. One is just a matter of notation that I'll be using going forward. And what that notation is going to be is shorthand for commensurable with, incommensurable with, commensurable in square with, and incommensurable in square with. What those are going to look like is these sort of semicircle shapes without the diameter. So if I write this symbol right here, like this, between two magnitudes, if I say A, this symbol B, then this means that A is commensurable with B. Like that. But if I flip this symbol, as I've done here in this proposition, this symbol means incommensurable. There's not really a standard symbol or shorthand for commensurable and incommensurable. The only one I've seen is one that Heath adopted, and this is what he did for commensurable and incommensurable. He did something a little bit different for commensurable in square and incommensurable in square. I've changed that a little bit, but it's functionally the same thing. So here, we have our symbol for commensurable with, incommensurable with. Now, if I write this, like this, so if I do the commensurable sign with the line under it, it means commensurable. I'll just write it like this, actually. Commensurable, that's not good. Commensurable in square, like that. Because the definitions lay out that there are some magnitudes, or rather some straight lines, this isn't true of all magnitudes, just straight lines, that are commensurable with other straight lines in square only, and other straight lines which are commensurable with other straight lines in both length and square. So sometimes we do have to make that distinction between commensurable and commensurable in square. And you can probably expect what incommensurable in square is going to be. It is going to be the incommensurable sign with a line under it. This means incommensurable in square, because we're also going to have to make that distinction sometimes between straight lines that are incommensurable with each other and straight lines which are incommensurable only in square with each other. Or not only with, but in square also. One last thing I do want to point out is how exactly this proposition would be used, because the enunciation doesn't exactly make it clear. I mean, how would you know that the remainder would never measure the one before it? The popular example of what this process would look like is we're going to have the isosceles triangle that we constructed all the way back in Book 4, Proposition 10. The one whose base angles are twice its remaining angle. And the values for that, if you're interested in degrees, would be 36, 72, and 72. The point is that ABC, for example, and of course these are going to be equal to each other because these are equal to each other. ABC and ACB are both double BAC. That's how we made this triangle all the way back in book 4, proposition 10. Now, why I bring up this triangle is we're going to use it as an example of incommensurable magnitudes. Because what we're going to find here is that the side AB is incommensurable with the base BC. How we would show that is we would cut off from the greater line AB a straight line AD equal to BC. So something actually like this. So these two lines will be equal to each other like that. Now, another thing that just common note of interest is that this line DC is equal to BC and AD. You can probably work that out on your own, but it has something to do with the fact that the base angles are double the remaining angle. But the point is that DC, just out of curiosity, is equal to AD and the base BC. So what this is going to tell us is that we're going to cut off AD, or we're going to rather measure AB with BC, but we're going to have some remainder DB, which is left over. Now the question for us is, does DB measure BC? Well, it doesn't. So we're going to do this process once more. From BC, we're going to measure a straight line equal to BD. In this case, you don't need to subtract it multiple times, just once is good enough. So we're going to have something like this, and BE will be equal to BD. And then we are going to join DE again like that. And again, if you're interested, this straight line DE is again equal to that, I believe. Actually, no, don't take my word on that. I actually have no idea what I'm talking about sometimes. But the point is, we're going to measure BC with BD and leave this remainder EC. Now, does EC measure BD, which came before it? Well, no, it doesn't. So we're going to continue this process again and again and again. And we're just going to verify empirically that there's never going to be a remainder which measures the one before that. So what this is going to tell us is that AB, the side AB, is incommensurable with the base BC. This is just a common fact. In fact, there are going to be a lot of incommensurable magnitudes with plane figures that we've constructed beforehand. In fact, a lot of the regular polygons are going to involve incommensurable magnitudes. By regular polygons, I mean those which we made in book 4. So polygons whose sides are all equal to each other, who are equilateral, and equiangular, whose angles are all equal to each other. This would be important for the pentagon because we know from the construction of the regular pentagon in proposition 411, it begins with the construction of this triangle. And then what you do is something like this, and then something like that, and then you eventually get the regular pentagon, like that. Something like this is how we do it in book 4. So what you'll notice is that the diagonal of a pentagon is incommensurable with its side, which is kind of interesting. And you'll notice this with a lot of the other regular polygons, that they have incommensurable lengths hidden within them. Perhaps the most famous example of incommensurable magnitudes, in fact, this is commonly believed to be the one that kick-started the entire idea of incommensurable magnitudes, is the diagonal of a square with its side. So if we have a square BC, then its diagonal BC is incommensurable with its side AB. Another example of incommensurable magnitudes hiding in regular polygons is the regular hexagon, which you might not expect because the regular hexagon is actually kind of nice. We know from the porism of proposition 415 that the radius of its circumcircle is equal to its side, so you wouldn't expect it to have something as ugly as an incommensurable magnitude in it, but alas it does. If you draw the regular hexagon like this, so say we have A, B, C like that, we have two sides of it, A, B, and B, C, and we join this diagonal right here, AC. AC is going to be incommensurate with the side AB or the side BC. They're both equal to each other, so it doesn't matter. So this is something you're going to notice about a lot of the regular polygons. This is going to be highlighted in fact, book 13, the last book of the elements, that our regular polygons have a lot of these incommensurable straight lines within them, which is quite interesting because you would expect regular polygons to be nice. In fact, the belief was that BC, the diagonal of the square, would be commensurate with it just because the square is so nice. And in fact, it was actually believed that there was no such thing as incommensurable magnitudes. But then came one Pythagorean who proved that the diagonal of the square is incommensurable with its side, and that sort of threw everything into hell. But I hope by the end of book 10, you'll appreciate incommensurable magnitudes, because right now they might seem kind of ugly. That you have magnitudes that have no common measure. I mean, that's sick, that's awful. But by the end of book 10, I hope that going through the entire book, and I hope I can demonstrate this, that there is actually something quite beautiful about them. And it's not only not a problem that they show up in regular polygons, the regular polygons might in fact be more beautiful for their incommensurable straight lines. But I'm getting ahead of myself talking about the end of book 10 and the beginning of book 13. We're just on 210, or 10.2, my bad. We're just on the second proposition of book 10. So we have a long way to go before we get to any of that. So because we have so long to go, I'm going to end the video here and move on to proposition at 10.3.